So we are so we have discussed about the solution of eigenvalue problems. Why do we do that? And we particularly discussed a simplified form of eigenvalue problem which serves the needs for most of the cases. Almost 99% of the cases, this undamped eigenvalue problem should be able to sort out all issues. Very pathogenic cases may be there where you need to consider the damped eigenvalue problem, and that is quite an involved exercise. I will not get into that. Maybe numerical methods course you will be dealing with that problem. So the purpose of eigenvalue problem is to estimate in the context of structural dynamics is to estimate natural frequencies, and the idea of using natural frequencies is of course to make use of response spectrum or design spectrum that is specified in the design codes. Earthquake excitation is specified in design codes in the form of design spectra. So you need to use that for calculating the forces, earthquake forces that you need to use in your design calculations. Right. So we have done that exercise, how to use response spectrum or design spectrum for seismic analysis of multi-degree freedom systems, and if we know the natural period or natural frequency, we can just read the maximum response of that particular at that particular natural frequency from the design spectrum, and then combine up with the mode shape associated mode shape vector, and with suitable modal combination rule we can find out whatever is the response quantity. So we will do that exercise. I mean, as an example, let us work out the spring forces and the reaction at the base using response spectrum or design spectrum. So do you have IS 1893 with you? IS 1893 is available for download from the Moodle page, course page on Moodle platform. Has anybody taken a look at that IS 1893?
Yes, sir.
Okay. Little bit. Okay. I recommend all of you to go through to read the code IS 1893 cover to cover. Don't leave out anything. Right? Many things, there are initial cases, initial few pages, there are glossaries, glossary of terms. So many things you may probably encounter for the first time, and if you don't understand anything, these lecture classes are the right forum to raise your questions and seek clarifications. Right? And the code, design codes are more of procedural aspects. I mean, they just tell you how to do that, how to do certain things. They don't really get into the philosophy of why are you doing this, or why this thing has to be done like this. So we, in this course, we would rather like to discuss the philosophy behind those provisions, why this is being done in this particular way, and for that it is important that you should know what the provisions are, uh, and those are not really very difficult. I mean, simple reading. So I expect tomorrow when you come back to the for the class, all of you should have gone through the code IS 1893. There is also one addendum which has been errata which has been issued recently. I will also upload that on the Moodle platform. Maybe I can patch to that code file itself, and you can use that. So, okay, fine. So I will postpone the discussion of use of code for estimating the design forces. Today I will touch upon another aspect. I mean, as a informal discussion, we will get into the numbers, specific numbers later. We have been talking about design for earthquake effects. What is the difference in designing for seismic effects from what you have been dealing with so far for gravity load design? Any guesses? Apart from the fact that there are lateral loads, I mean loads in horizontal direction that have to be taken care of. That is a given. Apart from that,
Sir, in seismic effect, the direction of force reverses, means sometimes it is positive, sometimes it is negative, as well as in gravity load, it always acts in same direction.
okay, fine. So that is one aspect. So the effect it will have is we will always have beams and columns, or we will not have anything as strictly columns and strictly as beams. Every element is a beam column. Every element carries axial load as well as transverse load, and undergoes flexure as well as axial deformation, irrespective of whether it is column or whether it is a beam. Right. So that is one change, one important influence. Second one is, of course, as Ravi mentioned, the directionality. It is reversible. So there is no such thing as main reinforcement and or tension reinforcement and compression reinforcement. So as far as we are talking of beams, we will have doubly reinforced beams, and we have to take care of both sides of the reinforcement, right? Because in one phase of motion, either top or bottom may be in tension. In the next phase of the motion, the roles will get reversed, right? And you cannot predict it. So we try to take the conservative route and provide whatever is the maximum reinforcement requirement, and do that accordingly on both the phases. So we will have all beams will be doubly reinforced beams. We will not be dealing with singly reinforced sections at all as far as earthquake resistant design is concerned. So that is one thing. Any other?
Sir, ductility comes into picture when
Yes.
you're designing for earthquake.
So where does the ductility come from? That's very important, and that's what I wanted to discuss informally today. I mean, just by way of discussion. I am not in the mood of writing any long expressions or anything, deriving anything today. So I will just try to discuss and ascertain this or try to understand this concept of ductility. How do you get ductility?
Sir, obviously the steel reinforcements contribute to ductility of the.
Okay, fine. Steel reinforcements are obviously concrete is not ductile. So, if we are talking about ductility, then obviously steel has to yield. And then, how does the steel yield?
Sir, when the deformation goes beyond yield point, then
Yes. So, some strain levels are required,
yeah.
isn't it? So, what is
Yes,
the
sir.
typical strain that we are talking about?
Uh, 0.87 FY by year.
Mm-hmm.
0.87 5 by S plus 0.002.
Okay. So, of course, the yield strain is one thing and the ultimate strain is another thing. So, when we talk of ductility, we are actually looking at this bridge, the plateau, yield plateau. How long is the yield plateau? Right? So, we look for as large yield plateau as possible. That will be the indication of large ductility in the system. But one thing that we all this discussion or this overemphasis on ductility due to steel, somehow we lose sight of the fact that strains are passed on to concrete. It's a compatible section. The bond is perfect. We assume the bond to be perfect, and strains are passed on to concrete. And tension compression, it's reversible. Right? So, there is really no chance of achieving ductility even if you have steel which is ductile enough, unless the concrete can cope with that kind of strain in compression. In at least in compression zone, tension we know it will not be able to cope, but the compression zone it should be able to cope with that kind of strain. Otherwise, you will not have any concrete, compression zone to build up any moment of resistance. So, what is the ultimate strain of concrete in compression?
0.003.
Yeah, 0.003, 0.003 or 0.0035, depending on which version you use. So, around that. So, now compared to this, 0.003 or 0.0035 strain, compression strain, maximum strain in compression of concrete, that provides hardly anything by way of ductility. Compare with the what is the yield plateau of the steel in this for this strain, almost negligible. From 0.002 to 0.0035, there is hardly anything that you can call as a ductility, great ductility that is being achieved by using high quality or special ductile reinforcing bar. So, how do we increase the ultimate strain of concrete? The concrete ultimate strain also has to be enhanced so that we achieve, the steel is able to achieve the requisite strain for yielding. Right? Now, that is where 13920 IS 13920 comes into picture. The special detailing provisions, reinforcement detailing provisions for ductile detailing as we call it. Now, what is this ductile detailing business? Uh, have you ever tried to um, break open something that has been under uniform compression from all sides? Do you understand what is hydrostatic stress? Hydrostatic component of stress tensor and deviatoric component of stress tensor.
Yes, sir.
So, what is that?
Sir, in hydrostatic compression, each and every part of the substance is subjected to compressive force in equal amount.
In equal
And
amount.
in soil also we study triaxial test. In that case, sigma 3 we consider as the confining state, that is hydrostatic pressure, and the deviator is the one we use on one side only, means
Yes.
generally longitudinally.
So, the point is the deformations are actually contributed by the deviatoric component. Hydrostatic stress, state of stress, when it is under uniform compression from all sides, so this system is very stable, right? There is no deformation at all. So any stress component, it is separated out into hydrostatic component and deviatoric stress component, and all deformations that you have, they will, or the failure that will happen in the system, that is only going to be coming from deviatoric component, right? So the reason I want to bring this into discussion is the confining pressure has a beneficial effect. I mean, you can also look at it from the pressure vessel. You must have done these problems of the hoop stresses in the due to internal pressure in cylindrical containment because of internal pressure. So, what is the hoop stress in the wall of cylindrical container because of internal pressure, let's say boiler or something, right? Just the any liquid stored in that. Now those hoop stresses or the carrying capacity or the with capacity to withstand the internal pressure increases if you can have an external compression over the entire container, I mean the confinement. If you tightly wound some kind of cable, pre-tension cable, and put kind of wind it very tightly packed, then you will find that your vessel is able to withstand much higher pressure than what it was able to do earlier without this confining pressure. So this is what the now you may ask me what has got this to do with reinforced concrete. We try to replicate this, we try to take advantage of this beneficial effect of confining pressure in the design of concrete section, and the confining pressure comes from stirrups or confining reinforcement as we call them. Now there can be different ways of having these stirrups or ties, lateral ties or transverse ties. We can have rectangular stirrups with cross ties in between, or we can have helical stirrups, helical reinforcement, or we can have circular ties arranged in circular columns. So there are different ways of doing that, but the effect of that is it is trying to hold together. Let's say this is a column, and if I confine it with the ties, then the concrete inside this, it is called the core. Outside this is of course the concrete cover, and it will fall off, so we will not be considering that in our calculation at all. So gross area is not used, gross concrete section is not used for calculation of forces or even the moment of inertia, because when we are talking about earthquake behavior, we assume that the concrete the cover has actually cracked and it is ineffective. It's only the concrete core which is contributing to the strength. So all our calculations should be based on the core concrete or cracked section as we call it, right? So core concrete inside, confined under the stirrups or the ties, transverse ties, that if I increase the confinement, then it binds the concrete core together, and then it is able to withstand much higher strain. And depending on how good the confinement is, the ultimate strain in confined concrete may be as large as 15 times the ultimate strain of unconfined concrete, what you are referring to as a 0.0035. So you may get almost 15 times increase in the ultimate strain of compression, ultimate strain in compression, bending compression in the concrete section, if you tie it, if you confine it properly. Right now, confinement of course requires that effect of confinement will keep on dwindling as you go away from the, if I have one reinforcement, one lateral tie here, its effect will be localized only around this tie. So if I want this confinement to be effective for a extended length of this member, then I need to have stirrups or these confining reinforcement steel at a closer spacing, so at a higher pitch, so to say. Right? So if I do that, then the effect of confinement will be more pronounced, and the concrete will be able to withstand much higher strain in compression. And your confinement, the stress strain curve, not just the ultimate strain, even the compression, the stress, maximum stress under compression, that will also increase. So it has lots of beneficial effects, and although we can work out the numerical effect of that using the theory of hoop stresses, but generally it is done in a prescriptive form. That's why IS 13920, that is for the ductile detailing code, is there. So that prescribes what is the minimum spacing of stirrups or minimum pitch of the helical stirrups, reinforcing confinement steels, that you should have in plastic hinge region. Please recall that I mentioned that we have certain zones where we encourage development of plastic hinges. The inelastic deformations are allowed, but they are allowed only in certain region. So I know a priori where the plastic hinges should occur, and wherever those plastic hinges have to occur, obviously I need to ensure that the section is able to achieve the ductility that I am assuming in my design calculations. Just by having a response reduction factor of R to bring down the seismic force doesn't give you the required ductility. Your construction has to be commensurate with your assumptions in your design calculations, and that will only come when the concrete section that you are using, that you are providing for, is able to achieve the kind of ductility that you are assuming. And that kind of ductility cannot come just by providing steel. Concrete has to withstand much higher level of strain in compression in order to be able to provide to cope up with that the kind of strains that are being imposed, right? And that will only happen when we provide special confining steels, and the requirement for that are prescribed in the IS code 13920, and the plastic hinge reason, generally it extends from top and bottom 1/4 of the span or the from the joint. So there you have you need to take care of this special provision that the confinement has to be proper, and then it's not just a matter of providing the stirrups. It also needs to be ensured that the stirrups do not open up during vibration, and that is why it is not just adequate to provide the confinement like this, right? It is not adequate to provide confinement like this kind of stirrup, 90-degree bend. One on this side it is bent at 90 degree, and on the other side it is bent at 90 degree, and then the entire system is enveloping, is tied to the main reinforcement bar, main flexural reinforcement. This is not enough, because during the vibration these will open up, and once this opens up, the effect of confinement is lost, completely lost. The concrete is no longer confined, and you cannot achieve, even if you have maintained that kind of spacing of the stirrups which is required for confinement. If the confining reinforcement opens up during vibration, the confinement is lost, and your section, your building will, or the section will not be able to provide the kind of ductility that was assumed in the design, and hence it will fail. So how do we do this? How do we avoid this? The key to do this is by bending the reinforcement stirrups by 135 degree. So instead of 90 degree, you bend it by 135 degree around a longitudinal reinforcing bar, so that it gets locked, it will not open up, right? So that's a very critical detail. Most of the buildings which fail during earthquake have this common feature. Reinforced concrete buildings, most of the reinforced concrete buildings fail because of inadequate lateral confining steel, and even if there is adequate confining steel has been provided, the construction supervisor was not alert enough to ensure, or he did not understand the importance of 135 degree bend in the stirrup, and he allowed this 90 degree bend, and when the earthquake comes, this confining steel was actually wasted money. It was as good or as bad as not providing that confining steel at all, right? So that doesn't help anyone. If you have if you have adhered to the close spacing of ties as prescribed in 13920, but you omit the detail regarding the 135-degree bend of the ties, because without this the stirrups would just open up and all this confinement or the assumption of confined concrete behavior would just be not valid, and the concrete section would not be able to provide the kind of ductility that has been assumed in your design calculation to bring down the force requirement, earthquake force requirement, and the building will collapse. Right? So, any questions? Similar provisions exist. I mean, the idea is only the ductility, and the provisions are there. I mean, even for steel buildings, you need to ensure that whatever ductility you are assuming in your design calculations, the actual construction can actually achieve that kind of ductility. Sometimes in steel structures, it is actually you will find the local buckling failure happening in the flanges, and you cannot achieve the ductility unless you have stiffeners available to prevent local buckling of the flanges. So we will of course discuss the issues with steel buildings later in the later part, but I am getting little nervous. 27 November is the last teaching day, and I am really lagging behind the course now. I need to gather the momentum and quickly get done with the topics that we need to discuss. So I need little bit of cooperation from your side. So please read the IS 1893 and 13920. Now I added one more code. I mean 13920 is a very small code. So very short document, very small document, and you can finish it very quickly. And it's, as I said, it's only a prescriptive specification. This is how the detailing has to be done. So what is the spacing and how it has to be done, right? So please go through these documents, and we will need these, try to understand those concepts, and if you have any problems, please discuss those in the class. If you are unable to understand any provision, anything that is there in the code, please discuss that in the class. Now we will take this approach. I mean, it's a design course, so the best way to learn that is by designing, learning through example. So we will take an example portal and try to example building and try to work out how to design it according to the code provisions, right? So how do we work out the seismic earthquake design forces using the design spectrum, and then what are the load combinations that have to be taken care of. I mean, the code specifies different ways the loads have to be combined, and then when you combine the different load combinations, you come up with the member forces, stress resultants, and accordingly those are the demands imposed, and you need to design the sections according to those forces, right? So with respect to earthquake, you just take the worst possible condition by taking either signs plus or minus because of the earthquake effects, whichever gives you the worst case, and then proceed with the design as you would normally do, right? So that's a standard, afterwards it's a standard design procedure. So we will discuss that, The only thing that may have to be, I'll try to delve little longer on the shear wall issues. Tall buildings, lateral resistance actually comes from, to a great extent, from provision of shear walls. So how do we integrate shear walls? I mean, again, just assuming that shear wall is providing you the lateral resistance doesn't actually uh, translate in actual structure. It has to be facilitated while the construction is taking place. So how do we integrate shear wall to behave as, or the structural walls to behave as shear walls along with rest of the structure, which may be a moment resistant frame? So what are the issues involved in that? How do we integrate? How do we ensure that the structure as constructed behaves in accordance with the assumptions that were made during design calculations? So issues are mostly similar for columns and shear walls, but shear wall has a little requires little more care for integration with the rest of the frame, and how do we ensure that? So from tomorrow we will start with a let me work out a problem, think of a problem which will serve to demonstrate or try to encapsulate all features that we may actually need to take care of during design. Typical problem, I'll take a building on hill slope. That will also bring in the problem of torsional coupling, where all columns are not of at the floor are not of same length, same height, and what kind of problems may arise because of that. So that's a very challenging problem for which no satisfactory solution exists even now. So most of the problems, I mean, you will find can be alleviated if you take care of the ductility provisions and the stiffness provisions, the lateral strength requirements to a large extent. And as the old adage goes, it is better to prevention is better than cure. So sometimes the problem is so difficult that you may have to actually look at unconventional unconventional approaches to build earthquake safe buildings, and that may involve using some of the seismic response control techniques. Right? Base isolation is the most popular one that is often touted, but that's only one of the possible solutions. There are several other approaches to do that. Several other devices are available from using which you can actually try to control the seismic response. So not merely by building the resistance of the concrete section or structural sections, you can also try to minimize the impact of earthquake motion on the structure, reduce the impact of the structure. I mean, it's just like trying to reduce the impact of a speed breaker while you drive a vehicle over it. That's the vehicle suspension. So that's a vibration absorber. So similar kind of systems you can deploy, you can design and deploy in a structural system which will absorb the energy of earthquake vibrations and bring down the requirement. Sometimes these are the approaches which help to a large extent in protecting very difficult buildings in a very difficult situation. if you have a very steep slope on hills, and if you have to build on that, then one has to look at these unconventional approaches to come up with a safe structural design solution. So more on these issues if the time permits towards the end of this course, but let us first concentrate on conventional strength based design, how to design a structural system which will be able to withstand the earthquake effects according to the assumptions made in design. That's very critical. You should always keep in mind that what you are designing for is a very, very reduced level of earthquake that a structure is expected to witness during its design life. Right? I mean, reduced level compared to what a structure is expected to witness during its design life. So if a design basis earthquake chooses to visit the area, then the structures are expected to sustain some damage, but that damage is intended to be in repairable range. The damage is supposed to be to the extent that it is repairable. The building can be repaired and put to use again. Right now, that can only happen if the construction practices adopted at site are in sync with the assumptions that were made during the design. So I just highlighted the kind of problems, the kind of oversight that may happen inside, and most of the cases that is the reason for failure of buildings during earthquakes. Not due attention is paid to implementing the design correctly on ground. Right? So I will stop here. Any questions? Anyone?
Sir,
Yes?
we have used one term as strength-based design. The actual design which we are going to do is strength-based design.
Pardon? Strength-based design is normal design. You estimate the force in the members and then try to provide make the section as strong as required. Right? You are not trying to reduce the demand by using some of the vibration control strategies.
Yes, sir.
Right? Any other question? Okay, fine. I'll stop here. Thank you. Please read both the codes before coming to class tomorrow. Thank you.